Moving 100 billion cubic meters of water 1,500 kilometers requires something most nations never attempt: re-engineering a continent's hydrology while the continent stays inhabited. China's south-north water transfer diverts water across 3 separate canal systems, each facing a constraint that made engineers reconsider whether the project was buildable at all. The eastern route had to lift water uphill 15 separate times. The central route needed a tunnel under the Yellow River wide enough to move a city's annual supply in weeks. And the western route still hasn't broken ground, defeated by elevation, permafrost, and the absence of a construction method that works above 4,000 meters. The promise was straightforward. The Yangtze River basin in southern China holds abundant water, while the northern plains around Beijing face chronic shortages. In the 1950s, Mao Zedong proposed borrowing water from the south to supply the north, a continental-scale version of interbasin transfers that had fed cities like Los Angeles and Denver since the 19th century. But those American systems moved water through gravity-fed aqueducts across relatively flat terrain. China's geography demanded something different. The North China Plain sits higher than the Yangtze Basin, separated by mountain ranges, floodplains, and the Yellow River, which already carried enough silt to clog any canal that tried to cross it. 3 routes were proposed, each solving a different piece of the hydraulic puzzle. The eastern route would follow the ancient Grand Canal north from the Yangtze Delta, threading through Jiangsu, Shandong, and Hebei provinces to reach Tianjin. The central route would pull water from the Danjiangkou Reservoir in Hubei province and send it overland to Beijing, bypassing the Yellow River entirely by tunnel. The western route, still on paper, would divert Yangtze tributaries in the Tibetan Plateau and send them northeast across Qinghai and Gansu. Together, the 3 routes were expected to deliver 45 billion cubic meters annually, enough to supply nearly 500 million people. The eastern route opened first in 2013 and immediately revealed the cost of moving water uphill. The Yangtze sits near sea level, but the endpoint in Tianjin is 65 meters higher. Over 1,200 kilometers, the route requires 13 pumping stations, each lifting millions of cubic meters per day. The Hongzhi Lake Station alone uses 6 massive pumps to raise water 15 meters in a single stage. Pumping that volume consumes enormous amounts of electricity, making the eastern route operationally expensive in a way gravity-fed systems never are. The alternative was building an entirely new canal across hundreds of kilometers of flat agricultural land, which would have displaced millions and taken decades. Engineers chose to follow the existing Grand Canal alignment and accept the energy cost. That decision turned hydrology into an accounting problem. Every cubic meter delivered north carried not just the capital cost of construction, but an ongoing electricity bill that would never end. The pumps run continuously during peak transfer seasons, drawing power equivalent to a small city's consumption just to overcome elevation. The central route presented a different constraint. It had to cross under the Yellow River without mixing the 2 water systems. The Yellow River carries one of the highest sediment loads of any river on Earth, more than 1 billion tons per year. If diverted water touched the Yellow River, silt would clog the canal within months. The solution was a pair of tunnels, each nearly 10 meters in diameter, bored 30 meters below the riverbed. The tunnels run for 4 kilometers, sealed with concrete linings thick enough to withstand the pressure of both the river above and the diverted water inside. Construction required freezing the surrounding soil to prevent collapse during excavation, a technique borrowed from subway engineering but rarely used at this scale in saturated riverbed conditions. The frozen soil acted as a temporary structural wall, holding back groundwater and silt, while tunnel boring machines advanced through the riverbed. Once the concrete lining was in place, the soil was allowed to thaw, transferring the load to the permanent structure. The technique worked, but it added months to the schedule and required precise temperature control across thousands of cubic meters of earth. When the central route opened in 2014, it became the longest artificial river in the world to operate entirely by gravity. Water flows from Danjiangkou Reservoir north through Henan, Hebei, and into Beijing, dropping 100 meters over 1,300 kilometers, an average gradient of less than 8 centimeters per kilometer. That shallow slope required meticulous grading and concrete-lined channels to prevent seepage and maintain flow velocity. The canal itself is open air for most of its length, making it vulnerable to evaporation, contamination, and seasonal freezing in northern provinces. To protect the water supply, China relocated more than 330,000 people from the canal corridor, demolished villages within the buffer zone, and imposed strict industrial and agricultural controls along the route. The resettlement represented not just a construction cost, but a permanent social restructuring of the corridor. Entire counties were depopulated, farmland abandoned, and local economies dismantled to create a sterile zone around the water flow. The decision prioritized water security over settlement continuity, a calculation that remains politically sensitive. By 2023, the eastern and central routes had delivered more than 70 billion cubic meters to northern cities, reducing groundwater depletion and stabilizing water tables in Beijing and Tianjin. But the cost exceeded initial projections. Official figures place total investment above $60 billion for the first two routes alone, not including annual pumping costs, canal maintenance, and the economic impact of resettlement. The price per cubic meter delivered made the south-north transfer one of the most expensive water supplies in the world, competitive with desalination in some cost analyses. The western route, designed to deliver 17 billion cubic meters per year from Yangtze tributaries on the Tibetan Plateau, remains unbuilt. The engineering challenge is straightforward. The source rivers flow at altitudes above 4,000 meters, and diverting them northeast requires tunnels through seismically active mountain ranges and permafrost zones where conventional construction methods fail. Tunnel boring machines operate poorly in frozen ground. Concrete curing is unreliable at high altitude and low temperature. Labor productivity drops as workers contend with altitude sickness. No start date has been announced, and no credible construction timeline exists. The project's environmental consequences are still unfolding. The central route draws water from Danjiangkou Reservoir, reducing downstream flow in the Han River, a Yangtze tributary. To compensate, the Yangtze to Han emergency diversion sends water back upstream during dry seasons, creating a seasonal reversal that ecologists argue disrupts sediment transport and aquatic habitats. In the north, increased water availability has allowed cities to reduce groundwater extraction, but it has also enabled continued urban expansion in a region where water scarcity was the natural limit on growth. Some hydrologists argue that the transfer delays rather than solves the underlying problem. Northern China's water demand still exceeds sustainable supply, even with southern water added to the system. The transfer bought time, but it did not change the fundamental imbalance between population, industry, and renewable water resources. Demand continues to grow, while source region hydrology becomes less predictable under climate variability. The system's long-term viability depends on constraints external to its engineering. The South-North water transfer succeeded as an engineering demonstration, but remains economically and environmentally contentious as a long-term solution. It proved that continental-scale interbasin transfers are buildable, even across difficult terrain, if cost and displacement are treated as acceptable trade-offs. But it also revealed the limits of supply-side hydrology. Moving water across 1,500 kilometers requires either massive pumping infrastructure or displacing hundreds of thousands of people to clear a gravity-fed corridor. Both options are expensive, irreversible, and dependent on stable source region hydrology, which climate change is already altering. The Western route's indefinite delay suggests that even China, which demonstrated the political and financial capacity to complete the first two routes, has reached the boundary of what continental water transfer can achieve with current construction technology. The delay is not political or financial, but technical. No one has solved high-altitude permafrost tunneling at the required scale, and the margin for error in seismically active terrain is too narrow for experimental methods. What remains is a partial solution. The eastern and central routes supply 40 billion cubic meters annually, enough to reduce, but not eliminate, northern China's water deficit. They function as industrial-scale infrastructure, requiring constant energy input, maintenance, and environmental management. The project's survival depends not on whether it can move water, which it demonstrably can, but on whether the economic and environmental costs remain tolerable as source region demand increases and climate variability stresses both the Yangtze Basin and the northern plains. The answer to that question is still unfolding. Visible now, not in construction milestones, but in water tables, reservoir levels, and the decision not to build the third route. The South-North water transfer works, but it works at a cost that few other nations have been willing to pay, and it works only as long as the South continues to have surplus water to send north. That assumption, stable and generous southern hydrology, is the final constraint the project cannot engineer away. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.